for the first task, I need to build an off mesh object from one of the provided mesh models. Okay, so bunny.ply, cube.ply, and torus.ply are like the provided mesh models, and I had to build an off mesh object. So that's in offab.h. My off mesh object is called main mesh, and to load my model I had to go to offab.cpp and then main mesh.load cube.ply. That's what I did in the start, but the issue was that I was not getting any output. I tried updating the draw function too, but it still didn't give me any output. The error was in the fragment shader. So in the fragment shader, the out call was not matching with the out color. That was already there by default. So I was not. After fixing that, this is the output I got, and it's a bit zoomed in like this because I still have not updated the. I think it was the vertex shader. Where's my vertex shader? My vertex shader over here. So this was the original code, and this is the output we get on if we run it. So the cube is there, but like it's fully zoomed in. So I had to put the MVP in, and then we get the cube object. Now for the second part of the task, we need to load some basic statistics of the model. So number of vertices, number of faces, bounding box, the center. Now for that, where was it? Offab.cpp. So first thing I did is I went to store all the vertices using the get vertices function. I stored it in vertices, and to print the first part is number of vertices. I just had to do vertices.size. That's how we get the number of vertices, and for number of faces we just need to use get num indices, and then I divided it by 3, assuming that we are using triangles for our rasterization. Yeah. So finally the third part is bounding box. So this is a vertices list, and then from there I break it down into vertex. Then I pull out the the vertex, the x coordinate of the vertex, and then I store the minimum in bounding box min. So similarly I do it for the xyz coordinates, and then bounding box max to find using the max function to get the maximum value. So that's how you get. So if you get the maximum and the minimum value, you will get like the bounding box for this task. And then finally there's calculate the center. That's the fourth part. For it I just had to take the minimum and the maximum bounding box and then divide it by 2. So let's check. This is a cube object and these are the statistics. So let's maybe load the bunny and check out the statistics for it. Yeah, 83,000 vertices and 14,000. No, that's 1,44,046 vertices. That's the bounding box and the center. I think, yeah, that's it for the first task. Now second task is go and render the torus model using GLSL, vertex and fragment shaders. So first thing is I have to load the GLSL. This my Phong shader. I call my off shader object, I called it Phong shader. So we just load vertex color. These are vertex shader and these are fragment shader. So use identity matrix for model matrix. So yeah, prepare the model. It's all retrieved from G underscore camera, and then okay. So as it said, I just retrieved all these values from G underscore camera. So model matrix, let's go look at the code in camera.cpp. So here I'm building the model matrix. So yeah, here this model matrix, and then it's actually step one. So first thing is we center everything. So that's basically a translation, and we put everything in the center. Then we perform scaling on it. Then we perform rotation, which is like our trackball matrix. And then finally we are allowed to perform. So after rotation we just do translation, and that's for the model matrix. Then I think the view matrix, it said we had to use the look at function for the view matrix. So yeah, I use the look at function over here, and let's look at offApp.cpp. So yeah, we need to remember this m underscore default distance is already 5, so it's the same as the one given in the question. Use 0 0 comma 5. So our m default distance is 0 0 5, so it's the exact same as this. Then the projection matrix, it says use GLM is to perspective. So first I had to go and look at like what do the parameters do of GLM perspective. So first we have is FOV y, which is like field of vision along the y-axis. Then we have our aspect. So that's like the aspect ratio. So like one aspect ratio value of 1, that would be like a square, which is like a 1:1 aspect ratio. Then we have Z near, that's like the nearest clipping plane on the Z axis, and Z far is the farthest. So what this means is that if it's lower than the if it's smaller than the Z near, then the object won't be visible, and if it's bigger than Z far, again it won't be visible. So that's the basic explanation of the perspective matrix, projection matrix. Here GLM is to perspective, and then I pass those same values. Then it says the torus model is rendered. It says to use blind form lighting model using a single directional light. This is what the output should look like, and let's run our project. Let me load the torus model first. Torus. Oh, I actually didn't reset my fragment shader, so it's looking a bit different. Actually, I need to explain those. Let me go and correct my code first. So this one, okay, this is correct. Yeah, the problem is with the diffusion amount. I think that should fix it. Yeah, so it's the same as the one in the output. The light direction is 1 0 minus 1. Okay, I'll confirm all those for you. So it says, where is it? Light direction 1 0 minus 1. Over here we have the same values. Light intensity 1 1 1. So this basically means 1 1 1. Then diffuse reflection coefficient, that's 1 0 0 over here. Mesh call is our diff amount, if you remember from the fragment shader. Then specular reflection coefficient is 1 1 1, which is this mesh spec call. And shiny coefficient, it's not mentioned over here, it's in the shader, it's in the fragment shader over here, 64. specular brightness. That's our shiny coefficient. So yeah, also so you remember my output was supposed to be like this. So to fix this, I had to use this hint over here. So it says calculate GL position in the vertex shader. Vertex shader is over here. So my original GL position was like this, and what that does is, let me run it again. So yeah, my model doesn't move anymore. To fix it, we need to apply the MVP transformations, and then that fixes our code. So yeah, then it says, it says to confirm that I have the fragment position in world space. Okay, let's go. The fragment position in world space. Frag world pos. This is how I calculated it. So frag world pos is this. Then it says the view direction. View direction is calculated by normalizing the. Here it's also already mentioned camera position minus the thing we just calculated right now, frag world pos, and then fragments normal in world space. So frag NRM. I think it's it's already multiply NRM with the normal matrix. And fourth is the light direction. Okay, the light direction should be given as a uniform variable. Here it is, uniform light direction, and it says light colors, diffuse, specular, reflection should all be as uniform variables. So all of them are over here. The color, the diffuse, the specular, and some other variables are all given as uniform variables. Now it says for the specular term, please implement both versions with and without n.l. Okay, it says to compare. So currently, let me first give you an introduction to, there's one part of the normal matrix which required explanation. Off-app.cpp, where is it? So in to do it says explain this. So why is the normal matrix calculated like this? So let me first break it down for you. So first is the math3 model. That's like extracting the upper left 3 into 3 portion of the model matrix. So say this is our matrix. The top left 3 into 3 part is for it represents the rotation, and the rightmost column that represents the translation. Then we need the inverse. Now if you remember in this model matrix we used we did centering, we did rotations, then we did translations. So to undo all that, we just had to we use the inverse matrix. So the inverse undoes all those translations, and then finally we need to use transpose because it's for confirming that the transformation is correct. It maintains the orthogonality and unit length. It ensures that the normal matrix maintains orthogonality and unit length. So it's basically for confirming that the transformation is correct. I think maybe I should go over model, view, and projection. That's in camera.cpp. So model matrix, as I said, we need to center everything, then scale, then perform rotation and translation. That's for the model matrix. View matrix we use look at, forgetting all those. Then projection. Yeah, I think I already explained all these. So okay, now it says implement both versions with and without n.l. Okay, let's go back to the code. Specular mount. Okay, so if we look at plane form reflection model, it uses the half-wave vector h instead of using only l. So original one says use n.l. Let me show you the output. This output is for n.l. I'll take a quick screenshot. I think the shading is actually not that bad. And this one is using the half-wave vector. So the shading is, I think it's a bit more. Now I think we can make a better comparison. So you can see like the shading is a bit more detailed. Like you can look at the opacity, it's like increasing a bit more. So let's call width, the width n.l, let's call it a simplified form model. It just uses the dot product of the surface normal and the light direction. And without n.l, which is the half-wave vector version, it uses the half-wave vector and the light direction. And the normal, surface normal. So half-wave vector is just the view direction and the light direction. And as we can see, the one on the right, it looks a bit more realistic. Actually, I think just the shininess a bit more, it makes it look more realistic. So that's for the comparison of the n.l. And then it says please implement directional light. For implementing directional light, first I have to pass the direction and color of the light as a uniform variable. So here light dir and light col, that's the direction and color of light passed as uniform variables. And then it says calculate the lighting and the fragment shader. So yeah, over here they use half-wave vector, uses light direction for calculation, then diffusion amount uses light direction, then yeah, I think even spec amount uses light direction in the n.l version. Yeah, so yeah, that's it for question for task 2. Now finally we have task 3. So basically we just need to implement rotation, zoom and shift. So first let me show you that it works. So this is the rotation. I'll rotate in all angles to show that it works. Then second is zoom. Zoom is using the right mouse. And finally is shift. It's for moving the object around using the middle mouse. So yeah, it works. Now let's go look at the code to understand how it works actually. So I think it's all in camera.cpp. So the hint given was M trackball matrix is a rotation matrix. I just need to calculate the rotation axis and the rotation angle. Using that I can get the M trackball matrix. So here we can see the P0 and P1 is already given. It's like the offset. So like if we move from one position to another position, so say initial position is P0 and P1 is like our final position. So this part was already given, and To calculate the rotation axis, I had to do the cross product of P0 and P1. Then I normalized it, and then calculate the rotation angle. I had to it's the negative arc cosine, which is like cos inverse of the dot product of P0 and P1. Then finally we get the rotation matrix, which is rotate of angle and axis, and that's our M Dragwall matrix. So that's for the rotation. Now let's look at zoom. Zoom is, we use something called scale. Scale is like using this we can control how big or how small that our object can zoom into. So let's say I don't want you to make my object smaller than half of its current size. So let's say 0.5. So yeah, look at it. It won't get smaller than half of the current size. M underscore scale equal to 100. Yeah, so that's all I wanted to explain. If I set it to 1, then it won't, I don't think it goes smaller than the current size, unless I make it bigger, of course. So yeah, I am trying to click on, but it doesn't get smaller. But if I make it big, I can make it smaller to the normal size. So that's how the zoom function works. And then there is mTranslation.x. Okay, that's for the shift. So shift is basically performing translation matrix. So it says generate a translation vector managed by the camera. This is basically it. We are just using m underscore translation dot x. X is for the horizontal axis and y is for the vertical axis. Okay, for the bonus, I tried implementing it, but I was getting a blank output. I tried using the transpose of the inverse of the model matrix, but it wasn't working, so I don't really know how to fix it. So I tried the bonus question, but it was basically the same blank output. So instead I tried implementing this was in your slide, half-life diffuse. So I tried implementing it. It says replace n.l by 0.5 n.l plus 1 square. To implement that, let's go to our fragment shader. Yeah. So it says float spec amount. No, not this. So it's our diffusion amount. This is the implementation of diffusion amount. It's the same as the formula back there. So 0.5 n.l plus 1 square. Let's see the difference. Personally, I think it just got a bit more brighter. Maybe let's try it on the bunny model. Where's my bunny? Offhab.cpp. Where's bunny Taurus? Okay, that's it for the project. Thank you very much.